Welcome back, my dear friends. A very good morning, good afternoon and good evening to all of you wherever you are. And as you know, this is the DADM2, which is Data Analysis and Decision Making 2 course under the NPTEL MOOC series, and this total course duration is 12 weeks, which is 30 hours, which when converted into number of lectures is 16 number, because each lecture is for half an hour. And as you can see in the slide, we are in the 47th lecture, which is in the 10th week. And after each week, which is 5 lectures, each being for half an hour, you have one assignment, and I am sure you have done pretty well in your first 9 assignments. So, we are covering the concept of reliability optimization and some concepts. So, rather than solving problems, it will be more very simple definitions related assignments, because this is quite involved. So, I will go slowly in order to explain you the general concepts. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, if you remember, we are considering the PMA and the RI approach, where the concept was you had in X space, which is room 1, U space in room number 2, I am just giving you the bullet points. So, whatever the problem solution is, or the problem given is, you first have the deterministic problem and consider the inputs based on the fact they are the mean values, solve them, you get some optimum values. So, you consider those optimum values, which technically should be the mean values. Using those mean values, you basically project them in the U space, find out the U values for x and p, use either the PMA or the RI approach, where either the disk increases its size until it reaches the boundary of the feasible region or infeasible region, whatever you say. In another case, the disk remain the same depending on a normalization value of beta, the boundary moves such that in both the cases, the moment it touches, you get the first optimum solution. Map it back to U space, again solve the iteration problem, the optimization problem using the methodology which you know. Find out the next set of x's and p's. So, x's are the values which you want decision variables, again map it back to the U space, continue doing it till the difference in the objective function values f of x is bounded by an epsilon value. So, now how you do it? So, in the generic reliability based optimization problem, you have that functional value of f I, where I is equal to 1 to whatever values of capital I you have, and this mean values which you have, the mean values which are blue in color, which I am now highlighting with yellow, these p values are the parameter values which are external, and this x are the decision variables. So, the mean values mean they are the mean. So, I will just draw it very simply. So, this was basically I will use only one color. So, it is easy for to explain. So, this is boundary, one of the boundaries, this is another of the boundaries. So, these are the mean values, the blue one and the green one are the mean values of x based on which you are trying to solve. So, now once you find out the values, so using the RI and the PMA method, you are trying to find out the most probable point MPP for x and p. Based on that you will solve. So, D would not have, because D is basically the deterministic value. So, once you solve it, you will find out the most probable point and the corresponding x value. So, remember one thing, when I am trying to solve it, I am trying to make a differentiation between the blue color and the red color. Red color I will consider the probabilistic part, the counterpart in the blue would be the deterministic part. But the issue is this x MPP is basically the most probable point in the U space, while its counterpart here would be the mu x and the values as it changes per iteration value. So, you have the constraints depending on the probabilistic constraints and the deterministic constraints, and obviously you know x is along the real line n dimension, d is along the again real values in the m dimension, and p is in the l dimension depending on the values of m, n and l. Now, if I consider from the diagrammatic point of view, so you are basically trying to solve the problem both from the reliability part as well as the robust part. So, robust you are trying to ensure that it will give you some very good solutions, as that perturbation values being there, the overall solution does not change much. So, there would be some variances, but the variability would be as low as possible. Let me put it in this way. So, what you want to solve is that you want to find out the areas based on the robust framework area and the reliability part. So, what you are trying to do, again I am considering the distributions in the very simplistic case to be normal. So, you will consider the robust feasible region for P2. P2 is basically the probabilistic external variable which is there. So, they can be P1, P2, P3 and the vector is P. Similarly, you will have basically the robust feasible region for P1 also. So, P1, P2 would give you the intersection which is hashed here, would give you the intersection based on which you will try to solve the problem. So, that will give you the common robust feasible region for P1 and P2. So, if it is a higher dimension, it will be a intersection. If it is 3 dimension, it will be intersection of 2 spheres or 3 spheres, and in the higher cases it will be intersection of the hyperspheres. Now, when you find out the nominal value is basically some mean value based on which the perturbation or the vibration is happening. Consider in this very simple way vibration of an atom. So, as the vibration happens, the overall area of influence would basically be dictated on the level of energy when you, if you know in very simple physics or chemistry. But what I am trying to do is that higher the vibration would basically mean higher the perturbation is, lower it is, less the perturbation is. That means, the variability is low, and in that case variability is high. That means, in the case where the variability is low, your reliable solution is much more robust and much better, in the sense that you can say with certainty that there is less variability. So, you have a nominal value for P1, similarly you will have a nominal value of P2 also, and the combined area of the robust region, depending, because why I am saying the combined region is basically it will depend on different type of constraints. So, the green area which I have drawn is basically the combined area, and the violet one and the red one are basically based on the perturbation of P1 and P2. Now, remember one thing, when you have the perturbations of equal values and you consider the simple concept of normal distribution, or consider that you are considering the concept of central limit theorem to be true, and you are bringing into the picture the concept of normal distribution, then the distributions which you have, let me draw it, then the distributions which you have, the univariate case for x or p, and x can be x1, x2, x3, or p can be p1, p3, it will be a normal distribution depending on the variability. Again, this is a normal distribution, and as already explained, variance being same, it will be a circle, variability being different, it will be the rugby ball depending on how high or low the variability is along x1 and x2 direction, considering you have x1 and x2 only. Now, it may so happen, okay, now as I said, I am repeating it again, that the variability being same and variability being different, whatever the case, if it is normal, then solving it using the standard normal deviate problem in the multivariate case is also simple. The moment it is non-normal, then trying to solve it using simulation method is the only way. So, you basically simulate it and try to find it out. Now, we will consider a very simple concept of multi-attribute utility theory, considering very simple concept of goal programming. So, okay, by the way, these solution methodologies I am not going to come, I am only giving you the simple background of robust optimization as well as goal programming. So, in goal programming, this is basically an analytical approach devised to address decision making problems where targets have been assigned to all the attributes. So, targets are there, attribute values are given, they can be high and low, and you want to achieve it some attribute value depending on what you think is the best. So, consider there is some concept of risk. Now, the concept of risk I am utilizing in such a sense that my level of satisfaction for attaining some goal would be definitely different from your level of risk or your level of satisfaction to attaining that goal. So, I am using the concept of risk or the level of reliability or level of probability, whatever you say. So, where the targets have been assigned to all the attributes and where the decision maker is interested in minimizing the non achievement of the corresponding goal. So, say for example, my goal is basically to achieve an attribute value for whatever decision it is, consider it is say for example, on a scale of 1 to 10 is 7. So, obviously, there would be variability. So, I want to basically minimize the overall variability of not attaining my goal. So, in other words, the decision maker seeks a satisfactory and sufficient solution with his or her strategy such that with minimum number of probability or chance that attribute would not be attained. Obviously, you cannot make it 0. So, if you think that each and every time that attribute level will be attained, that is not true, because there is a perturbation, there is a reliability, there is a probability or there is a dispersion. So, the purpose of goal programming is to minimize the deviations between the achievement of the goals and their aspiration values based on which you can achieve the best set of results. So, how would you do it? So, mathematically if you want to basically minimize the perturbation, what you will do is that you want to basically minimize the deviation between the functional value and the attainable value of the attribute which you have. So, what you will do is that for each value of function value of f1, you have an attribute a1 and you want to basically minimize the dispersion of f1 and a1, similarly from f2, a2 and so on and so forth. Now, I am not mentioning f1x or f2x, because x is basically a vector and can be done accordingly. So, I am only considering the functional form. So, what I want to do, so consider that actual value obtained, let me the black line, this is a1 value and there is some perturbations based on the fact that f1 can be between some a1 plus delta and a1 minus delta, and obviously the question would come that what if the perturbations are unequally penalized. Now, if you remember, I did discuss about some penalty functions and the Linux loss and the effect of that. So, again I will repeat those 3 examples. One was for the dam, building the dam. Height was actually should be 120, but you are building it to either 118 or 122. So, in that case, when if it is 118, the overall loss in the case when it was negative was much higher, because for the catastrophic loss. In the case if it is overestimated, then the level of loss would be less. So, obviously, the perturbations on 2 different directions will be different. In the case when you have the case for electrical circuit, the big electrical circuit which you have and the vacuum circuit breakers are there. So, if you overestimate the overall loss and if you basically replace those products later on after the guaranteed life on an average, then the overall loss would be much higher, because the chance of an accident is much higher. In the case when it is underestimated, then you replace the products more frequently. So, overall loss would be minimized, because you only stoppages and man-hour loss would be there, not any catastrophic loss. Similarly, you can formulate another problem where overestimation or underestimation would be equally penalized depending on the type of set of the problem which you have. Now, what you are trying to do is that you are trying to give weightages. So, the weightages, and again if you remember, for the unequal penalty loss, if it was a Lin loss function, so overall value. So, if you have this, I will use the same color for the functions. So, this underutilization is less penalized, overutilization is more penalized. In this case, underutilization is more penalized, overestimation less penalized, and in this case underestimation is equally penalized as overestimation. So, if you have, I am sure you have seen these diagrams when I have drawn. So, you will give, and they can be weighted. Weighted means you are giving some weights. So, these would be W1, W3, W1, W2, W3 depending on number of such those goals you have to attain. So, AI is the ith objective function which you want to attain, or the attribute, and Bj is the constant depending on the jth constraint values which you have, and you want to basically have the constraints accordingly, such the G1 is greater than equal to B1, G2 is greater than B2, and so on and so forth. So, what you want to have, so this is, so you have the constraints would be coming now. So, consider this is one of the constraints. I am drawing the simple linear constraints. The second one is this, then third one is this, then fourth one is this. So, now your, so note, let me use another one, wait, it will be easier for me. So, I will use this, and I will use the objective function with a black line. So, because the constraints have been given with different colors. So, this is the, just drawing the boundary. So, this is the feasible region, and what you have the constraints. So, constraint basically is a maximization one, it becomes maximum at, say for example, this is the point. I am trying to draw it as neatly as possible. Now, what I consider is that the attainable points are, the constraints are these fixed lines, which is A1, A2, A3, A4. So, I mark them as A1, A2, A3, A4, and I will give weights accordingly to those constraints depending on the level of importance. So, if I give the, if the perturbation is very low and the weights is also low, that means I would not be so much worried about the constraints being violated or not violated, because I have already considered in the objective function. What I have done in the objective function is basically to find out the difference between the attainable value. So, okay, by the way, these, okay, let me say these values are not the A's which I have for the objective function. So, these are, I am just mentioning them as A1, A2, A3, A4, but the actual functional form which is F1 minus A1 mod of that, F2 minus A2 mod of that, are that attainable value which you want to do. So, say for example, for the objective function which you want to maximize, you think for the cost you will minimize, for say for example revenues you want to maximize, you want to attain some level of value. Say for example, you want to attain a profit per month of 2 crores. So, that is the A value, and based on that what is the weight you will get. So, if for you, if you think that your level of attainment has to be done as minutely as possible, then the weights you will put accordingly would be high or low depending on what importance do you place on that objective function. So, one can use goal programming to address the issues of multi-attribute utility theory. So, let us consider in this way: assume k number of criteria functions are denoted by f1 to fk, and you basically club them into different groups. So, you have basically f1 to k1, then k1 plus 1 to fk2. So, whole set of k is being divided. Another set would be k2 plus 1 to k3, such that it is obviously true that the union or the sum of k1, k2, k3 is k. So, you have basically divided the whole set of objective functions into 3 groups, k1, k2, k3, and you will also consider why you are doing it, because you want to basically achieve some maximization, some minimization for them. So, if k1, k2 are only sets, so you will basically have the maximization sets as k1, the minimization sets are K 2. And we will consider, obviously there would not be any intersection set between K 1 K 2, they would be null set. Now, as per the problem, what is stated is that you will basically want to attain f 1 to f k 1, the respective values of these functions should be at least as large as b 1 to b k 1. For the other case, you will basically want to have f k 1 plus 1 to f k 2 as the respective functional forms somewhere in that set between the bounds which you put for yourself for the k plus 1 till k 2 sets of those objective functions, because what you have in the greater than sign you have b 1 to b k 1, then b k 1 plus 1 till b k 2, and then b, these k's I am mentioning in the suffix. So, it will be b k 2 plus 1 till b k. So, you want to achieve in different proportions and different values. For the b 1 sets, the first set, you want to find out them as large as possible. In another set, there would be some bound between which you want to attain, and for the third set, the function values should be at most, or the bound should be from the lower side. So, one is from the higher side, one has to be between a bandwidth, and another case it has to be from the lower side. So, what you are trying to do, if you consider this, some of the problems what you have, I will only write the functional form of G's, are greater than type. I am writing B in a very general sense. Some of them are the less than type, and some of them can be equal. But this equality I am basically putting it in a sense that there is a bound for that. So, for the greater than type, it will be b 2 plus infinity. For the case of the bounded one, I will basically have some b 1 to b 2. So, this b 1 b 2 would change accordingly, and another case it will be minus infinity and b. So, you have already divided the whole set into 3 regions: upper bound, lower bound, and some bound in between, based on which you will assign your values. So, remember, for any deviation from the restrictions imposed, there would be some functional weightages. So, if you remember the weightages which I had given, I had given weightages, or I would not say but generally the problem formulation has been done in such a way. So, the weightages are, for the first set would be W 1 to W k 1. So, these are greater than type. For the set which are in between, you will basically put an upper bound and a lower bound, because as you are putting an upper bound and a lower bound for the B's also, so similarly you will put an upper bound and the lower bound for the W's also for the next second set. And for the third set, there would basically be some W's based on which you will put the lower bound. So, what I am trying to do is, these are the bounds for greater than, these are the bounds for in between upper and lower values, and these are the bounds for the less than type. Now, this is basically makes some sense based on the fact that if you have taken the course TQM1 and TQM2, it basically gives you the upper control limit and the lower control limit. In some sense, it is like this. So, what you have is this. So, consider, I am not marking anything on the x axis and y axis. It is not very important from the problem formulation, but to understand it. So, you will basically have 3 regions and mark these regions with this color. So, this is the upper bound which you have, this is the lower bound which you have. So, what you want to do is, one set would be greater, so they may come here, so one set is in between. So, this dispersion over and below the mean time is not equal, need not be. So, this is for the second set, this is for the less than type. So, this will come here, and these perturbations, if I consider the normal distribution, where the area onto the left or the right of the mean would depend on the level of confidence. So, if I have 2 sigma plus sigma and minus sigma would give me the level of confidence as, say for example, about 67%, plus 2 sigma minus 2 sigma is the total width will be, plus 4 sigma would give me an level of confidence total area about 95%, and if I have plus 3 sigma and minus 3 sigma, it will give me the level of confidence about 99%. So, using this I have basically been able to formulate and divide into 3 regions: better, greater of attaining the attribute, in between I am satisfied, over another I am also satisfied, and less than I am satisfied, depending on the level of confidence I have for attaining that. So, I club them into 3 regions, and this I have already been talking about. So, in the first set, these are the values for which I want to basically minimize or maximize for the upper limits. These are the values, or let me use a other color, so it will be easier for me. These are the values for which I do it between bounds, and these are the values for which I do for above. So, based on that I formulate and I go for the solution method. Solution method I am not discussing, I am giving you the idea as I did for the reliability part and this part. So, with this I will end the second lecture in the 10th week and continue more discussions accordingly for the simple concepts. So, again I am mentioning these are a little bit difficult topics, we will only go through the simple problems for the assignments. So, with this I will end the class. Have a nice day and thank you very much for your attention.